Hello and welcome to the very first webinar from the Royal Institute of Navigation. Today's webinar is on GPS basics and will be presented by John Pottle, Director of the RIN. Future webinars in this series will cover other satellite navigation systems as well as alternatives and augmentation systems, so do keep an eye on our website and social media channels to find out when these webinars will take place. I'll now hand over to John for the presentation.
Okay, hello everybody and thank you for joining. So here are some questions that this webinar aims to address. It really is a basic starting point orientation to what is GPS, how does it work, how many satellites are there, who controls it, how accurate is it, and so on. So GPS is one of four so-called GNSS systems, Global Navigation Satellite Systems. The others being the Russian system GLONASS, the Chinese system Beidou or North Star, sometimes called Compass, and the European system called Galileo. This video, however, will just focus on GPS. So first of all, where are the GPS satellites? Well, this is a very basic diagram, but just let me explain. So in the center here, we've got the Earth, and this is approximately to scale. So I've got the Earth in the center, and this large black dotted line around the outside is what's called the geostationary arc, sometimes called the Clark Belt after Arthur C. Clarke, and that's 36,000 kilometers from the center of the Earth. So roughly speaking, the Earth, I think, is 12,700 kilometers in diameter. So 36,000 kilometers out, Arthur C. Clarke discovered that a body in orbit would have the same period of orbit as the rotation of the Earth, so 24 hours. And that allows communications satellites to be positioned in a stationary orbit above the equator. That's not where the GPS satellites are. The GPS satellites are indicated on this green dotted line here. And this is known as a medium Earth orbit, or MEO, you may hear it called. And those satellites are approximately 22,000 kilometers above the Earth and orbit the Earth in approximately 12 hours. So they're not stationary above the Earth. In fact, they move very quickly in different orbital planes. If we come back right towards the surface of the Earth, just to orientate you a little bit, the blue band indicates the orbital height of, well, you'll have heard of some of these. The space shuttle would typically orbit at between 300 and 500 kilometers. So just compare that to 22,000 kilometers for the GPS satellites. Totally different ballgame. International Space Station as well, about 400, 410 kilometers. And you may have heard of a satellite phone system called Iridium. It's now being used for other purposes than just phone calls, potentially positioning in future as well. That's about 780 kilometers. So you've got, so in summary, you've got in this band close to the Earth here, you've got Iridium, the International Space Station. It's the orbit in which the space shuttle would have flown. The GPS satellites, and indeed the other ones I just talked about, the other GNSS systems, are in this 22,000 kilometers arc. And the geostationary satellites, communication satellites particularly, are 36,000 kilometers above the Earth. One other thing I'll come back to, which I'll just mention on this diagram, also close to the Earth is the ionosphere and troposphere. So the signals from the GPS satellites travel down quite unperturbed for about 21,000 kilometers, and then they come into the ionosphere and troposphere, and that does cause some disturbances, which I'll come back to later. So the GPS system at the moment has 31 operational satellites on orbit. And as indicated in this diagram, they are in orbital planes around the Earth, such that at any one time, a receiver, as indicated here, with an antenna, as indicated here, would be able to see somewhere between 7 and 8, maybe 9 satellites at a time. So that's how many would be visible from the surface of the Earth at any one time. Yeah, those 31 satellites, I won't go into too much detail here, but they cover different series of satellites. The oldest ones are the so-called Block 2R, and then I think there are 11 of those at the moment. And then there are some modified satellites which start adding additional signals, including new signals for commercial users. Block 2 are modified. So about half of the satellites at the moment are, well, actually more than half are Block 2 and Block 2R. And then we've got some newer satellites in the constellation, Block 2 follow-ons, and a couple of the new GPS-3 satellites. As well as the so-called space segment part of GPS that we've just been talking about, there are two other segments, so-called segments, the ground segment or the control segment, and the user segment, which is where we and all of our mobile devices and other GPS receivers come in. The control segment, as you can see indicated from this, this diagram from the GPS Directorate, is really quite complex and quite global. You can see at Schriever Air Force Base in Colorado, over here on the left. This is where the master control station for GPS is located. And just a little bit further west in California, Vandenberg Air Force Base, is where the alternate or backup control station is located. And then you can see well spaced around the Earth, these little blue dots, monitor stations. So there are well spaced around the globe monitor stations with reference receivers that monitor on a 24/7 basis the health of the constellation. And this is no small deal, the control segment. In fact, for the new GPS-3 satellites, the whole control segment has been upgraded and also made more resistant to cyber attacks in a project called OCX, a huge software project, which has had its snags, but is now beginning to come on stream. So with that combination of the satellites and the control segment, you've got the basics, all the basics you need to fly the satellites, to upload the latest information and data to them, and to monitor their health, and if necessary, move them around, take them out of orbit, bring new satellites on, and so on. So that's the backbone, if you like, of the GPS system. So what about the signals? Well, this chart here is actually a snapshot of the UK, frequencies within the UK. And just to orientate you a little bit, so from left to right, at the left-hand side, 10 megahertz, you've got relatively low frequencies. Moving right through to the right-hand side, 3 gigahertz, you've got really quite high frequencies. GPS is just about in the middle of that. I'll come back to that in a second. But what are these other signals here? So you will be familiar with these. You will use some of them, and you will recognize them. There's a cluster. First of all, let's look at this one here up at number 10. There's a cluster of signals. This is around 2.4 gigahertz. So these are the different Wi-Fi signals. And incidentally, microwave ovens are also around 2.4 gigahertz. But hopefully, with the door closed, you wouldn't see that. You wouldn't see the radiation coming out of a microwave oven. So there's a little cluster of signals there at number 10. If I go right to the left-hand side of this chart, number 1, this is actually FM radio in the UK, about 90 megahertz. And then number 2 and indeed number 4, these are digital analog radio in the UK. And then there's a whole raft of these other higher power signals which are related to mobile telephony, so GSM and also 4G LTE. So 5, 6, 8, and 9, here we are. 5, 6, 8, and 9 are all mobile. So well, the highest power one, incidentally, number 3, that's Tetra. So that's emergency services mobile. So where in all this mix is GPS? Well, the answer is the GPS code, the course acquisition code, spreads out the signal, and the power density of the GPS signals are actually below this this block at the bottom. This is the thermal noise. So the signals are what you call down in the noise. Very low power indeed. For comparison, this number 7 here, which is just to the right, just a bit higher frequency than the GPS. This is the Iridium satellites. And remember on that first chart I showed how much further in those to the Earth, how much closer to the Earth those Iridium satellites are. The GPS much further away, and the signals down in the noise. Illustrating that just in another way, a 500 watt power from a GPS satellite is attenuated by 180 dBs as it travels down to the Earth. And that's approximately equivalent to your average old-fashioned car headlight in Australia being looked at from the UK. So very, very low power indeed. So how on earth does a receiver work? How does it acquire these signals? How does it find them in the noise if you can't see them? The answer is, the detailed answer is a bit beyond the scope of this presentation, but let me just try to summarize it as simply as I can. So the receiver is indicated in this diagram by the blue lines at the top and at the bottom. The satellite signal, the code coming down from the satellites, is indicated by the red line. And as indicated, they're digital signals. The trick is that the receiver needs to create a replica of the signals that are generated from the satellites, and then undertake what's called an acquisition search. So the receiver searches both in the frequency domain and in the code domain to align itself with the signal. So the replica in the receiver aligns itself with the code coming down from the satellite. And when that alignment is achieved, both in code and frequency, the signal to noise ratio, the correlation, if you like, between the signal from the satellite and the replica from the receiver is good enough that the signal to noise level, or signal to noise ratio, is at a usable level, and you can acquire or lock on to the signal. So in very simplistic terms, that is some of the clever stuff that's going on in the receiver. And you can see that indicated here. So in the top half of the diagram, the blue arrow, the receiver is trying to move itself around in the code domain, but also in the frequency domain. And the bottom half, there you go, it's locked on, it's got correlation. You can use the usable signal to noise ratio, and you can acquire and correlate and lock on to that signal. Once you've got 4 of those, you can get a position and also time. So a 3D position, latitude, longitude, and height. The reason you need 4 is that you need to resolve time as well as position. And you might, when you're locked on, you might see something like this on your smartphone, the blue dot. So these blue dots, as indicated here, indicate a GPS, maybe even other constellations, but for the sake of this presentation, a GPS lock. So you've got your 4 satellites when the sort of zone of uncertainty, that blue zone around the blue dot, is fairly tight. Maybe the one on the right is a slightly less accurate position, maybe not such good satellite geometry, or maybe some sort of blocking or risk of multipath has been detected in the receiver, so you've got a little zone of uncertainty. The one on the left, I would suggest, is a GPS position that's got good visibility of at least 4 satellites, and hence very good accuracy. So how good is the accuracy? I actually really love this chart. It's from the GPS Directorate. They don't seem to produce it anymore, so if you're listening, GPS Directorate, I for one would love to see it back. This one is from September 2018, and if anything, the wonderful job that the GPS Directorate does, they've slightly improved its performance, I believe, since here. But the takeaway is that whether you're looking at the best week, the best day, the worst day, the performance of the satellites, the satellite accuracy is less than a meter, single frequency, as received on the surface of the Earth. So in the real world, you don't get a meter of accuracy. And the reason for that is a number of factors. One of the major ones being the atmosphere that I mentioned earlier. So these signals, particularly with a single frequency receiver, have to travel through the atmosphere, and that introduces variable delays depending on time of day, solar activity, scintillation, and other effects, and typically could cause errors of a few meters, which is why when you hear about, well, how accurate is my simple in-car navigation system, the answer would typically be, it's a few meters. It's certainly not 1 meter. It's not better than 1 meter. It's typically a few meters. Same with typical single frequency cell phones. Maybe 5 meters is a good rule of thumb if you've got a good visibility of the satellites. There can be factors that will degrade that, and I'll touch on them a bit later. But that's a good rule of thumb. So, is it true to say that more satellites give you better positioning accuracy? Well, I would suggest the answer to that is yes and no. So, if you are in a situation where you've got an open sky, just looking at GPS, and you've got good visibility of the 7 to 8 satellites that I mentioned, you should get the performance of typically around 5 meters single frequency. There are, however, reasons that more satellites can be better, and this is indicated by this diagram that I'm showing here. So just to explain that, if we take a look at the blue line, I hope this is coming up okay for you. If we take a look at the blue line here, you can see that it's wandering around compared to the track, which is more indicated by the red line. So the person here was walking on the sidewalk up and down the road. So the blue line's a bit off. And the reasons for that is that there are buildings that are both blocking the signal and also reflecting the signal. So the blue line shows the performance with just GPS. And you can see that there are times in that motion sequence that the positioning accuracy is really not very good at all. The red line, on the other hand, is the GPS satellites plus another constellation, GLONASS. So I'm going a bit beyond the scope of this presentation, but I hope this helps to explain it. If you add GLONASS, which is another 7 to 8 satellites, so you've got approximately 14 satellites, you can see that the receiver has always got 4 or 5 or more satellites with good visibility and good geometry, and that's the key reason why that red line is more true to the track than the blue line. So in summary, in the open conditions, 4 satellites with good visibility is fine, but when you move into more challenging environments, such as an urban environment, then it can be advantageous to have more satellites. We'll return to that topic in a bit more detail in a future webinar where we talk about GPS working in tandem with other satellite navigation systems in what's called a multi-GNSS environment. So then, just to finish off this GPS basics presentation introduction, what about dual frequency GPS? You may have heard that this is now coming into cellular phones, car navigation systems. It's being looked at to improve accuracy for autonomous vehicles, for example. And there are several advantages to multi-frequency. So what we're talking about is the legacy code and signal, if you like, which is the L1, the one I've been talking about, the coarse acquisition code. So that's on one frequency. And then there are two other civil frequencies available on GPS now. So L2C, there are quite a few satellites with that on board, and L5 is not fully built out, but it's beginning to get to usable levels. So when you have two frequencies, you can actually measure the atmospheric delays and therefore back out completely that ambiguity. There are also a number of other advantages, possibly the most notable being that the L2C signal is a higher power, and therefore you can lock on or acquire signals in more challenging environments, such as indoors, for example. And you can also sometimes acquire signals more quickly. So there are a host of advantages, but the takeaway really within the scope of this presentation is that by going from one frequency to two frequency, you can improve the accuracy from the approximately 5 meters I mentioned in good conditions down to 1 meter or better. So a very useful improvement in accuracy. So there will be further information on other satellite navigation systems and also other areas in our future videos. We're going to cover the vulnerabilities of satellite navigation, some of which are naturally occurring, such as the atmosphere and multipath signals, some of which are simply human error, such as segment errors in the bottom left of this chart, and some of which are intentional disruption, like spoofing, interference, and cyber attacks, ranging from casual hacking right up to very motivated and highly sophisticated attacks. So we'll be covering that in a future webinar. Also in future webinars, we'll cover how different sensors are fused together to give you a blended position. So it's very unusual today to just use GPS on its own. And as indicated here in a typical cell phone, you'd also typically benefit from multi-GNSS, as well as Wi-Fi positioning, cellular positioning, and also the built-in compass and accelerometers within the phone. And increasingly coming on stream now, the cameras, bottom left, for what's called visual odometry. So we'll aim to cover many of these in the rest of this webinar series. But for now, that concludes the GPS basics. I hope you enjoyed the webinar, and I hope to see you in a future video. Thank you very much.